Hello everyone. Today I'm going to present to you about a new product that I built after learning about a very significant problem in especially complex systems, whether it's a startup or a large tech org or any system. And that is like for understanding why systems break and how we detect it safely. That is why I'm going to present to you OpsLens. But I build it to explore how software behaves over time under load and under failure and how we can detect problems early and safely. I'm sure if you are a founder of any large system which is complex, or any engineer or any owner who might have this idea, then you might be able to understand what I mean. So let's see the problem first. Then I would love to show you a product demo which actually works, and I can give you a demo of how it works. Most engineers start with this belief. It's completely reasonable if the logic is correct. If the tests pass, then the system should work. But this belief quietly assumes that software lives only inside code. By the way, if I haven't introduced myself, my name is Roshan Sharma, and I have been trying to build some very meaningful, impactful um, software solutions and products, ideas, visions, and so on. Recently, especially using latest AI agent tech tools and technology and tech stack in order to build really secure, scalable architecture and softwares. This is one of my attempts to help any developer, any engineer, and any large org or any org with complex systems, especially in tech, which could, or anything that's use text. That would be a better word because it would be very relevant. This presentation is for everyone, whether you're technical or non-technical, and that also means that I would be um, explaining you in depth so that a layman can also understand. So this presentation would be one of the longest I ever built, but the idea is to have a very information, no, very um, easy to understand, easy to consume, um, learning content technically. In reality, systems fail in production all the time, not because engineers are careless, but because software doesn't run in isolation. So the real question is not who wrote bad code. The real question is, why do things break even when everything was programmed correctly? So when I was very much interested about this subject, about systems in general, because recently I had attended my own system analysis and design, classes in my university before I graduated. Like it was in my last trimester, and I always wanted to do something related to what I studied passionately. And one of those problems which I saw, which has a very big value, which could be solved using especially the AI agents and so on, is that I got to know that code lives in logic, system lives in reality, right? And the reality includes time, traffic, networks, hardware, dependencies, and people. And reality is never static, right? So that is a problem. Time is the first enemy of software. Over time, memory fragments, queues grows, um, cache fills, clocks drifts, and data pattern change. The code doesn't change, but the system does, right? One of the most dangerous assumption is that the load increases linearly like this. In reality, systems often look healthy until suddenly they don't. Latency spikes and queues explode long before errors appear. Errors scream, latency whispers. A system can be technically up while users are already suffering. Most monitoring tools don't treat latency as failure, and that's a problem. Traditional monitoring usually answers one question: is the system down? But the more important question, which I feel, and that's where I'm going to present you my software idea, and product to detect if is the system degrading. The gap is where real incidents are born. So we need better signals. And the problem is not theoretical. According to Gartner, the average cost of IT downtime is around $9,000 per minute. And for large organizations, it can exceed $1 million per hour. Observability failures are expensive failures. Amazon found that every 100 millisecond of latency cost them about 1% in sales. Google found that more than half of the users abandon a page if it takes longer than 3 seconds to load. Users feel pain long before systems logs errors. Traditional dashboards. So traditional dashboards are usually made up to, just give red and green lights, but they are bad at showing trends, degradation, and risk. By the time alarms fire, users have already noticed. In 2021, Facebook experienced a global outage lasting nearly 6 hours. There was no bad deploy, no single bug. The failure emerged from systems interactions, not code correctness. This is the kind of failure OpsLens is designed to reason about. Introducing OpsLens. OpsLens is my response to this reality. It's a local observing and incident response system designed to understand system health, not just report failures. OpsLens watches a real running service, not synthetic metrics, not fake dashboards, a system behaving under real conditions. Instead of raw logs, OpsLens produces clear health states: healthy, degraded, or incident. This mirrors how humans actually reason during incidents, right? The core flow is simple and intentional: system to data to signals and decisions. Everything else is OpsLens supports. Everything else in OpsLens supports this pipeline. The diagram shows the full OpsLens architecture. Telemetry flows into durable storage. Signals are computed deterministically, and both. Give me a second. I'm all right. Telemetry flows into durable storage. Signals are computed deterministically, and both humans and AI consume the same canonical truths. Here's again a detailed version of the system architecture, which I have also published in my GitHub repo, which I'm not sure. I think I might open source this so that everyone could leverage it. But when I'm not sure. But anyways, I'm still trying to build this 100%, which works. Anyways, the observed service stimulates a real backend. It handles health checks, workloads, latency, and failures just like production systems do. So, what we are going to witness today in this whole content is basically um, um, I will be showcasing my product in which we will be simulating a real backend which I actually developed. You cannot study failures without creating it, right? Like if there is a question like why are we even simulating that, like why I'm going to showcase you something simulating in not real life, but we have to study failures in order to improve that and become resilient and better. OpsLens intentionally introduces latency and errors to observe how systems degrade over time. Every request is measured, success or failure, nothing is ignored. This ensures we don't lose the truth of what happened. If it's not stored, it's not truth. OpsLens persists. All telemetry, so metrics can be produced, reproduced, audited, and trusted. Raw data is noise, signals are meaning. OpsLens converts raw telemetry into health signals humans can reason about. The system classifies health into three states: healthy, degraded, and incident. This removes ambiguity during stressful situations. Incidents are not moments, they are periods. OpsLens detects sustained unhealthy behavior, not transient blips. I built OpsLens because I wanted to understand how systems actually fail, not just how we imagine they fail. I used OpsLens to simulate load inject failures and observe how the system behaved under stress. And this is the results which I found. OpsLens detected two distinct incident periods, a 14.29% error rate, and significant latency, as you can see, latency degradation, as you can see. These were not obvious without structured signal. So as you can see, there are 34 requests which were observed, two incident periods detected, 14.29% of error rate, and about 439 milliseconds of 95th percentiles of latency. And OpsLens generated quantified insights, not just opinions. OpsLens gave me clarity. I could see degradation early, understand causes, and trust the conclusions. So this is what OpsLens actually do. It gives, clarity and proactivity so that we could sustain and build better systems, resilient systems. And this is basically some of the tech stack that I use primarily. Each technology was chosen deliberately. Fast API for observability, SQLite for durability, Streamlit for human context, and OLlama, AI for safe local AI. Yes. So I use Meta's OLlama, artificial intelligence model. You can use any one else. If ever I do open sources, most probably, yeah, I will do, so that everyone can use it. So you can use your own APIs as well, LLMs. But the idea was to have something local and very safe, and something where systems could be built better locally, so that everything is secure technically, right? Metrics are not magic. Every number is computed from stored data using deterministic maths. Yes. This is some of the math logic which I use, which is, not too crazy, but it's something to understand. That's why I put this as an example here. So the error rate is simply failed request divided by total request, right? So I wanted to make it transparent, simple, and reproducible. So this proves that this is very transparent, reproducible, and very logical and rational. Like there is nothing vague. Like everything is very, very measurable and everything is happening. Average height pain percentiles revealed. That's why OpsLens prioritizes percentile, 95th percentile and 99th percentile latency. So as you can see, that's what we try to do here. And same data, same result always. So it's not vague. We can actually determine if there are all the same parameters and conditions every time, then yes, the result should come same. Now, incidents can be triggered by errors or latency, right? A system can be unusable even if it's technically up, which is so true. As you can see, some of the latency threshold and error threshold which I put here. And yeah, systems, even though if they're up, even though if you are online and YouTube can run, but if it cannot load the thumbnail, for example, there is a problem. Even if the video runs, but there is a problem, or even if the video loads later, then people might just exit YouTube, and I don't really know where would they go, but anyways. So uh, maybe some other software apps. Anyways, AI is powerful, obviously, but it can hallucinate as well, right? So using AI carelessly in production systems is very dangerous. We all know that. Softwares like companies like, yeah, Rabbit CLI, Code Rabbit, and these kind of companies, why did they come, like Copilot? I think they have a review system and so on. because using AI can be dangerous, malicious, and so on. So we actually made sure, like in OpsLens, AI explains all the technicality, whatever the system discovers, the AI is used for being explainable and so on. But code decides. So the AI never computes metrics so that it do not hallucinate. But definitely, I think we can come up with different kinds of combination of how code and AI can work together. For example, you might know recently, Microsoft is trying to hire, or might hire, I don't know, hire someone to replace their entire code to Rust, for example, and using AI and so on. So uh, you know, definitely AI would be used and can be used in order to do that safely, probably, but the systems need to be mature, so we need to be safe. So that's why, in order to calculate and have very, very predictable outcomes, we are using AI to explain what is happening so that people could understand, even though if they are technical, less technical, or non-technical, and so on. The AI copilot helps engineers understand what's happening and what to investigate next safely. So any engineer don't really have to use their brain technically. They can actually understand using AI. Okay, this is what happening. Maybe you should do this. And we will witness this in today's demo, by the way. This project demonstrates systems thinking, production engineering, discipline, and safe integration. And the approach applies to tech companies, governments, and any critical systems where failures matters. Yes. So technically, it applies to any critical infrastructure where failure matters. What happens if it fails, and so on, right? So I hope you got the whole idea. Again, before starting my demo, if you would like to connect with me in LinkedIn, you can definitely scan this QR code, right? And if you want to just schedule a call with me, I would be more than happy to talk about this system which I have been building, or anything that you are building, and happy to discuss and you know see where it goes. Now let's go to the demo. All right. So as you can see, this is a basic dashboard. Um, so we wanted to have a human in the loop, so that they could observe, and here are all the options. Um, let me start telling you by, give me a second, please. All right. So, all right. So as you can see, this is hosted like in the local host 8502, for example, and this is the OpsLens, dashboard where the user can use it to observe anything happening with their another service system, for example, another system. And the key idea was basically that UI does not compute metrics, it only renders canonical signals derived from stored telemetry, and human in the loop is there for observing that, right? Because there is a reason which I emphasize here, is that UI is not a source of truth. We don't want the dashboard to accidentally lie, right? Now, as you can see, this is the target service URL, and here is the time window. Here is the collector run, which collects all the information, so on. Before that, I would like to show you, like, these are some of the tools that one can use if they ever use my software, my system. Is that this is the system which is being observed. This is the backend which I created just for this demo, which is actually running, mini backend technically. And what I mean is, OpsLens is basically a doctor, as I think we might have discussed earlier, that it's a or doctor for the patient, where it's the back end right now, which we are trying to observe and trying to understand if there is some problem, if it will degrade and so on, right? Um, so this, you can see the JSON response of the page, and it exposes mainly two endpoints, right? One is for health, for basic liveness checks, and another is work to simulate, real workloads with controllable latency and error rates. So these are some of the endpoints, and now this is, as you can see, this is the OpsLens backend service interactive API. And this, it shows exactly how the endpoints behave, what inputs we can use to simulate failures. As you can see, like, here is the simulated work endpoint that we discussed just now. And here are some of the parameters like latency, error rate, and so on that can be used in order to, simulate work endpoints and so on. Right, now let's go to the dashboard again. As you can see, this is the OpsLens dashboard, and here are the target service URL, which is basically the system which we are observing, as we saw just now, right? So the collector, as you can see, here's the collector run, right? The collector generates traffic to this target, but the dashboard itself reads from the database. Okay, so here are many of the collector instances, and here we can see what I built is the time window, and it has several time intervals, so that, the time window basically controls how much recent history we analyze. So if it's like last 5 minutes, 15 minutes, 60 minutes, or you can even customize when you use your ID directly from the terminal and so on. And signals like, error rate and P95 latency are computed only from telemetry inside this window. All right. um so this was the time window. Now, as you can see, right now we haven't really run this because I wanted to save this for um, the demo part. But just for sake, like, here we should know what is the condition of the system right now, the key metrics, the total request, error rate, P95 latency, availability of the system. It says all systems are operational because it's working on real time. That means since we haven't really run anything, that's why it's showing 0, and availability is 100%. That's why it's saying 100%. So there is nothing dummy, to be very honest, in this demo. So here comes the performance over time, endpoints breakdown, incident history. And as have told you, like, I have used Llama model to have local AI capabilities so that everything remains secure as a system. Even though if it's a demo, but this is just a demo for anyone who might be interested to use it, I would be more than happy to connect with them. And these are some of the recent requests which I made. As you can see, these are all, uh, you know, today it's 20. Okay, so it's not 26. I don't know if that was the issue. Maybe it's working with UTC time zone and I didn't fix that. But anyway, so yeah, that's why it's showing 12, 32, and yeah, that may be the reason. Anyways, so now we will just go to our terminal and show you how it works. So suppose we have the collect telemetry module from Python, and we have set the duration for around 120 seconds. And now we just need to wait for some time, for example, and let's see if it works. So what does telemetry, OpsLens telemetry collector does is basically it goes and collect all the metrics and parameters that it has been working with. So we exactly know if everything is safe, secure or not, if there is a latency, if there is some kind of other rates, as I have shown you, right? Like the API endpoints and so on. So it basically calculates the simulated workload, and if there is any problem, let's wait for a few more seconds. Hopefully it works. It should work because it worked. But anyways, all right. So mode change to degradation. All right. Hopefully we get some good information about our system, if it's working um, or not. So as you can see, here are the exact process what you need to do. Technically, you just have to, start the observation service, that is the backend, if you remember, and or any system that you are trying to test. Um, this is our observed backend service. It simulates a production API with realistic workloads and failure modes technically. You can verify the service if it's healthy and start the telemetry connection. This, as you can see, we got something. So as you can see, there were a total requests of around 34, error count of 1, and um, error rate of this, and other telemetric metrics technically, which will be used. Now what we can do is um, we can have, as you can see, we got nearby simulated. Now we will just create a health report, for example, and here is the health report. This is the health report of OpsLens health, right? OpsLens. So the status, it says it's incident, and it also shows, when was it last updated, and so on. So this is a proper report, and it says there is an incident detected. Check the service logs for errors and so on. Now let's launch this to the dashboard. So once we run it, we should see it in our dashboard. All right. So as you can see, our OpsLens software, our product, was able to actually run and be tested on a simulated workload of a backend which I built. And okay, so here is the latest date. So as of 8:50, which is the correct time, oh sorry, 10:50, I'm sorry, um, 25th of December, this was reported as an incident. There were total 34 requests made um, within those backend service, and there was an error rate of this, and 95% latency of this, and availability of this much. So our system was able to calculate those stuff. Now, here are the metrics. There is no time series data available for the selected window at the moment. So right, so there is, since we only had for like, I guess, 20 seconds, so there is nothing to actually have as a time series data. But anyways, so the endpoint breakdown is, you can see here, we also get a report which is the endpoint. For example, health, total request was around 11 and the errors were 0, but for work it were like 23 and 1, there was 1 error. So this comes with this much of error rate, and this is the latency. So it's pretty transparent and very, very easily verifiable. The incident history is also recorded. As you can see, there was an incident, this was a time, this, and the duration was around 5 minutes, for example, um, because it was by default set into 5 minutes. So, all right. So we have all this data. These are some of the recent requests, as you can see. Oh, okay. Some error. Shit. Let me just try this again. There was some again. This is a very good example of what we face. All right, we have this here again. Now we have all this complex information. Now what we will do is we will use our local AI LLM, which is currently Meta's Llama, and we will click analyze, and our local LLM is able to actually process all this information and ingest and give us a very actionable insight and very understandable actions and insights for anyone. Let us take some moment to see what it comes out. Meanwhile, it as it comes, what I would like to say is, if you are interested to learn more about this product, or if you think this can actually solve your problem of your organization, do let me know. I will be more than happy to have some pilot tests so that it could be beneficial. Because you know my goal at the moment is to build scalable, secure, architectured systems which could actually be very valuable, which could bring value to anyone. So I would be more than happy to do that. Let's wait for some more time. Hopefully, our local LLM model is able to analyze and give us some insights, what happened and what to do, probably, and so on. As it happens, probably, I would like to show you my GitHub repo of how I um, OpsLens, and this is my GitHub repo. As you can see, I built this entirely using Python as a programming language. So see, understand, and act on production systems is what OpsLens does. OpsLens is a local production inspired, system which can help us to observe and do incident response, for example, with an agentic AI copilot, which we are, doing it right away. And there is, you know, the agent is still working to get the output. Let's wait for some more time. Till then, we can discuss about this GitHub repo. As you can see, what it is, where we can report, have an incident response, observe what's happening, simulate, and so on, that demonstrate how modern engineering teams detects failures and extracts deterministic health signals and safely use AI for operational reasoning. Why OpsLens? Most monitoring tools focus on collecting data. OpsLens focuses on turning operational data into decisions. Modern systems fail in complex ways, latency degrades before error spikes, incidents occur without obvious signal causes. Engineers need fast, trustworthy summaries during on-calls. That is so true, right? Like that's actually hitting the pain point uh, of several engineers. OpsLens was built to demonstrate how telemetry becomes durable data, how data becomes deterministic signals, and how signals can safely inform AI-assisted reasoning. This was my whole agenda of building the entire system so that I could demonstrate my expertise, so that, how we can do all this stuff. This is the overview, the overall architecture overview. where there comes a service, which is basically the backend service as I showed you. Then it goes through a telemetry collector and it takes all the information and so on. There comes a database where I store everything, and there are signals which we get, and that is also showed up in the dashboard. And there is an AI copilot powered by Llama at the moment, because it was open source and free and local to be safe. And that's how the basic architecture is there, and this is how it works. And this is the core engineering principles are used. Like, all health signals are computed, tested, and reproducible. Metrics are computed by code. AI only interprets outputs. Operation safety first, failure-aware design, local zero-cost execution, no cloud services or paid APIs required. To very honest, yeah, it's actually zero cost. So yeah, and these are the measured outcomes that you saw live. And also I put that. So the whole idea, how many however times you execute this, you will get the same results for the same system with the same conditions. That is the condition. All metrics are derived from persistent telemetry and validated across CLI health reports, streamlit dashboards, and automated tests that we all saw. Here is the reliability and validation you see. So this is what it happened. OpsLens was built with test-driven validation across layers, automated tests, which had basically 15 tests in service layer, 14 tests in data and persistent layer, signal extraction and incident detection, 12 tests, and so on. Edge cases covered like empty databases, service unavailability, and latency on the incidents, partial telemetry, and AI copilot unavailable. So these were some of the parameters that were used to validate and verify every single step that we did right now. The AI copilot, as we also, is safe by design. It receives only pre-computed signals, so there is no chance of hallucination. It's all about natural language processing, and the AI model is actually able to help users understand, which we will be seeing soon. This is the basic tech stack of what I used. This was whole programmed using Python programming language, fast API for the observable backend service, SQLite for durable telemetry storage, which we did, Streamlit for human in the loop dashboard, as we saw for the dashboard, technically front end, OLAMA local LLM for agentic reasoning, and PyTest for automated validation. So this is what I demonstrated. So the area was mainly production engineering, infrastructure and systems, data engineering, reliability, AI systems, and software engineering. I mean, thanks to all the AI agentic tools available right now, I was able to actually build an entire system where I could, demonstrate my production engineering skills, for example, incident detection, health states, graceful degradation, right? Similarly, for infrastructure, layered architecture, deterministic signals, data engineering, telemetry pipelines, index schemas, reliability, SRE, right? Site reliability engineering. So these were some of the stuff, AI systems and software engineering, where we could test, config, discipline, structured logging, and so on. So everything is available in the docs if you want to read. And this is it. Now let us see. So finally, around 10:53. Now it's 11:01. So it was generated just today at 10:53, 34 seconds by using model phi 3. And as you can see, this is this incident summary. So the OpsLens system has experienced an incident where the 95th 95th percentile latency spiked to around 460.4 milliseconds, which is above a predefined threshold of concern at or above 400 milliseconds. All right. This indicates a potential performance issue affecting response times within the last 15 minutes, since time window began from 10:43 p.m. to 10:53 p.m. All right. So as you can see, it was totally off, 10 minutes time frame window. Um, Likely root causes. So our AI model is also able to interpret like what is the root cause. Likely an increase in load or traffic has resulted in higher latency as indicated by 95th percentile latency of over our threshold, and the total request count being at its highest within this time frame, 34 requests. The error rate is also elevated 2.94. This suggests that system resources are under pressure, likely due to unexpected surge in traffic or resources. Our AI copilot is also able to um, help us understand like what are the immediate mitigations technically. So number one, scale out the affected services. If auto scaling is not already triggered, an available capacity can handle additional load without degradation of performance further, as this could elevate uh, pressure on system resources temporarily while investigations are underway, right? It's a good idea. Temporarily divert traffic to a standby or replica instance if one exists that has been idle recently but it's capable and ready to for increased demand until the issue can be fully diagnosed, ensuring critical functionality continues without interruption as much as possible while maintaining system stability and so on. So these are few of the steps. Next, debugging steps. Investigate recent deployments or changes in infrastructure configuration to determine if any could have impacted performance. Examine the work endpoint, right? Log specifically for errors and latency patterns during this time window, and it shows a higher error rate compared to others. For example, there are a lot of other inference that one can get, and for the conference, it says this AI existential analysis engineers must validate all suggestions before taking actions on production system, which is but obvious that we have to be careful as an engineer. These were some of the recent requests. I have been trying to build this system from many hours now. So it's like three, perhaps it's working on UTC time zone right now, which I did not, put time to, make that as per EST, for example, where I'm located right now. These were some of the latencies which, based on different telemetry collection happened into different backend, which I was testing throughout while building the entire system. So I hope this was very meaningful. Now we are ending this call. This was one of my longest meetings ever. I mean, like longest presentation. The whole idea was to explain you the problem, why it is there, why it's happening, and the solution which I came up with, and the entire product demo, the software demo, where I executed and showed you how I engineered the whole product, how I, applied data engineering, software development, and other tools and techniques with a reliable infrastructure and AI systems, infrastructure systems. I hope this was useful and something meaningful. If you'd like to give me any kind of feedback, again, I'm always open to discuss. I'm always open to improve. This was one of my efforts to build meaningful solutions for complex systems. Thank you. See you in the next one.